Let's discuss Unit 1 solutions. There are m points on one straight line AB and n points on another straight line AC, none of them being A. How many triangles can be formed with these points as vertices? They have given two straight lines, naming them as AB and AC. So let's take this to be AB. We'll take AC from the same point of A. There are many points here and the total number of points in this line will be M. So let's take this as M1, M2. Points will be from 1 to M. And if you take the other line AC, there are n number of points. We'll name them as N1, N2. So the count will be 1 to N. Now the question is, how many triangles can be formed with these points as vertices? If you take 2 points from AC and 1 point from AB, you can form a triangle here. And when you take 2 points from AB and 1 point from AC, you can form a triangle here. A triangle can be formed by, the first way is, I have to choose 2 points from AC and 1 point from AB. So the first kind of triangle that we have just seen. And the second point will be 2 points from AB and 1 point from AC, the second one. We have to apply combination here. The reason is, only when I have the number of ways to form a triangle, I can finally count the number of triangles. So in this aspect, 1 will be written as, there are totally n number of points in the line AC. So n points on AC and I have to select 2 points, which will be NC2. 1 point from AB will be, there are m number of points on AB and I have to choose 1 point. This can be represented as MC1. So NC2 is from the line AC and MC1 is from the line AB. Now how do I actually represent this first point? Will be NC2 into MC1. This will be the first set. And the second set, 2 points from AB. So this can be written as, AB will have m number of points. So MC2 into 1 point from AC. This will be NC1. The number of triangles will be the sum of 1 and 2. 1 can be written as NC2 into MC1 plus 2 can be written as MC2 into NC1. NCR is equal to n factorial divided by r factorial into n minus r factorial. Now n will be equal to n and r will be equal to 2. So this is n factorial divided by r factorial is 2 factorial, n minus 2 factorial into m factorial divided by 1 factorial into m minus 1 factorial plus MC2 will be m factorial divided by 2 factorial into m minus 2 factorial into NC1 will be n factorial divided by 1 factorial into n minus 1 factorial. So we will solve this separately so that it will be clear for you. Now let's see how to write this n factorial. This can be written as n into n minus 1 into n minus 2 factorial. 2 factorial and n minus 2 factorial. So divided by 2 factorial will be 2 into 1. So it is 2 into n minus 2 factorial will stay. So I can cancel this and this will give me n into n minus 1 divided by 2. So I will just place the same here, n into n minus 1 divided by 2. Now m factorial can be expressed as m into m minus 1. Why do I expand this? Is just to cancel them with the denominator. So this will be 1 factorial into m minus 1 factorial. This will be 1 factorial is again 1 and we have m minus 1 factorial. I can cancel both and this will give me the value of m into m plus. m factorial divided by 2 factorial into m minus 2 factorial. This will give, so since we have m minus 2 factorial in the denominator, we will make it as m into m minus 1, m minus 2 factorial. Divided by 2 factorial will be 2 into 1, 2. Then I have m minus 2 factorial again, I cancel this, and we have m into m minus 1 by 2 into n factorial divided by 1 factorial into n minus 1 factorial. So now we will write this as n into n minus 1 factorial divided by 1 factorial is 1 into n minus 1 factorial. So I am cancelling both and bringing this to n. This will be n. Now since this is just multiplication, I can make this as m into n minus 1 divided by 2 plus same here m into m minus 1 divided by 2. Now what is common in these two parts will be m into n divided by 2. So I am bringing m into n by 2 outside. Now what will be inside is n minus 1 will be written as it is. This plus will be retained. Then I am mentioning m minus 1. So this will give me m into n divided by 2. Now this can be rewritten as m plus n, and when you add minus 1 and minus 1, we will get minus 2. So now you can find option 2 to be exactly matching with this. Option 2 will be the right answer. Next question, find the sum of all 4-digit numbers formed using the digits 1, 2, 4 and 6. They have given a formula to do this. N minus 1 factorial into sum of the given numbers into, you have to multiply with the number of ones. How many ones will be there means n number of ones will be there. Here you can take n to be the number of digits. So 1, 2, 3 and 4 digits are available here. So n is equal to 4. The sum of all digits will be 1 plus 2 plus 4 plus 6, which is equal to 10 plus 3 will be 13. So the sum of the digits will be 13, and if you have 4 digits, it means you have to use 4 number of ones here. So now taking this to the formula, I have 4 minus 1 factorial into sum of numbers will be 13 into 1 1 1 1. This will give me 3 factorial into 13 into 1 1 1, and 3 factorial will actually expand to 3 into 2 into 1 into 13 into 4 ones. 6 into 13 will give me 78. 78 into 1000 will give me 86,658. So this will be the answer if you know the formula. So this is the usual way if you don't have any idea about the formula. Now there are 4 digits 1, 2, 4 and 6. When you want to form a 4-digit number, it can start with 1, it can start with 2, it can start with 4, it can start with 6. If you want to know how many numbers will be totally formed with these 4 digits, I have to use 4 factorial. That is 4 into 3 into 2, 12 into 2 will give me 24. There will be 24 4-digit numbers. Now let me start with 1, 2, 4, 6. I have an option to swap 6 and 4. So 1, 2, 6, 4. Now I have to swap this part. So now I will bring 4 to this side, then 2 and 6 here. Then I have 1, 4, 6, 2 here. Now I have to bring 6 to the second part. So 1, 6, 2, 4 and 1, 6, 4, 2. When I add this, I will get 8, 6, 6, 4. There are 6 4-digit numbers here. So 6 into 4 will give me 24. Now we will start with 2. I have 1, 4, 6. Swap the last two. 2, 1, 6, 4. Then bring 4 to the second place. 1, 6, 2, 4, 6, 1. 2, 6, 1, 4 and 2, 6, 4, 1. Now when we add this, we will get 14, 4, 4, 2. Now we'll write down the number starting with 4. So it is 4, 1, 2, 6. 4, 1, 6, 2. Bringing 2 to the second place, 2, 1, 6, 2, 6, 1. Bringing 6 to the second place, it is 1, 2 and then 2, 1. Adding up all this, we will get 25, 9, 9, 8. Now starting with 6. 6, 1, 2, 4. 6, 1, 4, 2. 6, 2, 1, 4. 6, 2, 4, 1. 6, 4, 1, 2. 6, 4, 2, 1. And the sum will be 37, 5, 5, 4. Adding up all these will again result in 86, 6, 5, 8. Option number 1 will be the right answer. Next question. How many integral solutions are there to x plus y plus z plus w is equal to 29, where x is greater than or equal to 1, y is greater than or equal to 2, z is greater than or equal to 3 and w is greater than or equal to 0. For integral solutions, the number of solutions to x1 plus x2 plus till xr is equal to k. For this equation, the number of solutions will be k plus r minus 1 c r minus 1. So this will give the number of solutions. How should the equation be? It will be in the form of x1 plus x2 plus xr is equal to k. So there will be r number of terms and k will be the constant in the right hand side. There are 4 variables, namely x, y, z and w. We have to change this to x1, x2 format. We will first rearrange this part. X greater than or equal to 1 can be written as x minus 1 greater than or equal to 0. I am introducing a variable called x1 which is equal to x minus 1. Now this will result in x is equal to x1 plus 1, where x1 is greater than or equal to 0. Why do I rewrite in this way? It is because I have to bring this equation to this format, only then I can apply this particular formula. Y greater than or equal to 2. This can be written as y minus 2 greater than or equal to 0. So I am just bringing the 2 this side and just making this as 0. So since I have started with x1, now the next variable will be x2. So y minus 2 will be x2. This means x2 will be greater than or equal to 0. Now how do I write y using x2 is x2 plus 2. Now z, it is greater than or equal to 3. So the same thing we are doing, z minus 3 greater than or equal to 0. I am introducing x3 here, which will be z minus 3. And now this can be written as z is equal to x3 plus 3. So obviously when we substitute x3 to z minus 3, this will mean x3 is greater than or equal to 0. So let's take the main equation here. X plus y plus z plus w is equal to 29. X can be written as x1 plus 1. Y can be written as x2 plus 2. Z can be written as x3 plus 3. Let's take this w to be x4. We'll just label it as x4 here, which is equal to 29. x1 plus x2 plus x3 plus x4 is equal to 29 minus 1, 2 and 3 will give me 6. So 29 minus 6 will result in 23. The equation will be x1 plus x2 plus x3 plus x4, which is equal to 23. This is in the form of x1 plus x2 plus xr, which is equal to k. From this you can take the value of k to be 23 and r to be 4. We will find the number of solutions. So it is k plus r minus 1, c r minus 1. So let's substitute these values here. K plus r minus 1 will be 23 plus 4 minus 1, which will give 26, and r minus 1 will give 4 minus 1, which is equal to 3. So this will be 26c3. So this is in the form of ncr. So this will be n factorial divided by r factorial into n minus r factorial. Now it is 26 factorial divided by 3 factorial into 26 minus 3 factorial. So 26 minus 3 will be 23 factorial. I will rewrite 26 factorial as 26 into 25 into 24 into 23 factorial divided by 3 factorial can be written as 3 into 2, and this will be 23 factorial. I can just cancel this. 3 8s are will be 24 and 2 4s are will be 8. 25 into 4 will give me 100 and 100 into 26 will give me 2600. Option number 2 will be the right answer. Next question. Let n denote the set of all natural numbers. R be the relation defined by a comma b r c comma d if ad into b plus c is equal to bc into a plus d. They are asking us to find whether they hold one of the properties or all the properties that exist in equivalence relation. To test for a reflexive, usually we represent a comma a that belongs to R for all a that belongs to the set A. So R refers to the relation here, and when I mention capital A, it means the set. We cannot check it with A because there are two elements involved in both the left hand side as well as the right hand side. So this can be written as let A comma B relation A comma B. This A will be the same as this A. Instead of this, I am using A comma B. Wherever C comes, I have to substitute it by A, and wherever D comes, I have to substitute by B. Now I have to put it in this form. So AB into A plus B, which is equal to BA into A plus B. Since it is multiplication, I am just converting this as A into B, A plus B. So both these sides are same, and so reflexive property is there. Now we will check for symmetric property. For symmetric, we have if A comma B belongs to R, then B comma A also belongs to R. For all A comma B that belongs to the set A. So let us take it as let A comma B relation C comma D. Use the same equation here, AD into B plus C, which is equal to BC into A plus D. Now just bring left hand side to the right hand side and right hand side to the left hand side. So BC into A plus D is equal to AD into B plus C. Now just swap these two. C into B, D plus A. Both will be equal only, but we are just swapping and writing. Similarly, DA into C plus B. What will this give me is C comma D relation A comma B. If A is A comma B and B is C comma D, the swapping C comma D relation B comma A is also existing through this. So in this way we are proving it to be symmetric too. Once when you prove it is symmetric and reflexive, automatically there is only one option from the following that you can choose. So it will be definitely an equivalence relation, which means transitive property can also be proved. So before testing for transitivity, once you are sure of reflexive as well as symmetric, you can mark the answer to be option number 4. Now we will check for transitive property. This is the usual format that we give, and for this problem we are using this. Okay. So usually how will we write transitivity is if A comma B that belongs to R and B comma C that belongs to R, then automatically transitive property will say A comma C will also be in R, and this is for all A comma B comma C that belongs to A. We will have to take two sets. So let A comma B relation C comma D. This is for A and this is for B. And then we will take another set. Let C comma D relation E comma F. This is B and this is C. So let's start with this part here. A comma B or C comma D can be written as AD into B plus C equal to BC into A plus D. Now just multiply them inside. ADB plus ADC equal to BCA plus BCD. This has AB and this has AB. So just write it as ABD plus ABC. This should be written in the form of CD. This is ACD and this is BCD. Let it stay. Now bring this to one side. So AB into D minus C, which is equal to, bring this to the other side, which will give B minus A into CD. We will write this in the form of AB divided by B minus A, which is equal to CD divided by D minus C. So let's mark this to be equation number 1. We'll do the same thing for this particular relation. So instead of A, B, we have CD. Instead of CD, we have EF. This will result in CF into D plus E. You can work it out and see in a slow manner. I am just writing this. So wherever I have A, I will place C. Wherever I have B, I will place D. Wherever I have C, I will place E, and wherever I have D, I will place F. CFD plus CFE, which is equal to DEC plus DEF. So I'll just change this as CD in one way. So F will stay here and I will make it as EF here. And similarly it is CDE and DEF will stay as it is. So CD will be in one side, F when E comes this side it will be E, which is equal to D minus C into EF. And this can be written in the form CD by D minus C, which is equal to EF. We can name this to be second equation. From 1 and 2, what we get is, we have A into B divided by B minus A is equal to CD D minus C. So what is CD D minus C will be this one. So this will be EF divided by F minus E, which says that the right hand side has a value in my second equation with another two variables. So this will say AB divided by B minus A, which is equal to EF divided by F minus E. When you have AB divided by B minus A, what is it from? It is from A comma B. So let me have A comma B relation. EF divided by F minus E is from E comma F. So I am placing this. When we have A comma B relation C comma D and C comma D relation E comma F, transitivity will show that A comma B will be in relation with E comma F. So this is the usual A, B, this will be the B, this will be the C, and now A will be related to C. So this is how we have proved this is also transitive. So in this way we are proving it to be an equivalence relation, but you need not go for this part. So once you prove reflexive as well as symmetric, you need not check for transitiveness due to the options given like this. Next question. A is equal to 4n plus 2 where n is a natural number. B is equal to 3n where n is a natural number. Which of the following is correct for A intersection B? Now let's have the set A here. When n is equal to 1. So 4 into 1 will give me 4. 4 plus 2 will give me 6. Then n is equal to 2. 4 into 2, 8. 8 plus 2 is 10. Then 4 into 3, 12 plus 2, 14. Then 4 into 4, 16 plus 2, 18. When it is 5, it is 22. When it is 6, it is 26. When it is 7, it is 30. Next we will come to B. B, it is actually 3 into n. 3 into 1, it is 3. 3 into 2, 6. 3 into 3, 9. 3 into 4, 12. 3 into 5 15, 3 into 6 18, 3 into 7 21. We will have 3 comma 6 comma 9 comma 12 comma 15 comma 18 comma 21 comma 24 comma 27 comma 30. Now A intersection B will have 6. Intersection in the sense the element must be present in both A as well as in B. Then we have 18, then we have 30. Now what we will be doing is we have to check all these numbers and see which set is matching with A intersection B. So let's take n here, then we'll have 12n square plus 6n value here, and then we'll find it out. So for n is equal to 1, 12 plus 6 is 18. So it starts with 18 and it misses 6, so 1 will not be the answer. Then we have 24n minus 12. So 24 into 1 is 24, minus 12 is again 12. A intersection B doesn't have 12. So this is also out of the race. Then we will go with 60n plus 30. The first number itself is in 90, but the previous number 6, 18, 13 less than 90 are not found. So this will also not be there. Now we will check for 12n minus 6. So when n is equal to 1, it is 6. When n is equal to 2, 12 into 2, 24, 24 minus 6 will be 18. When n is equal to 3, it is 36 minus 6, it is 30. So 12n minus 6 has the set 6, 18, 13. So minimum the first 3 elements are taken from this particular expression. So we go with option number 4. 12n minus 6, n is a natural number, will be right for A intersection B because both have the same set of numbers. Next question, let G is equal to real number difference 0 and H is equal to minus 1 comma 1. Let them be the groups under the multiplication. Then the mapping from G to H is defined by this. What is this? Basically, we have to understand one thing. R is a set of real numbers. Real numbers in the sense you can have both positive, you can have negative, you can have 0, everything. So in short, let me give it as negative, 0 and positive numbers. We have a denotation called R star. The R without 0 is R star. What is this R without 0? When you have the set R cannot be multiplicative. They have given it is a group under multiplication. So R cannot be multiplicative in the sense when you have 0, any element multiplied with 0 will give you 0. Excluding the 0 from the real number group, we are mentioning R to be a group under multiplication. G is equal to R divided by 0. This means R difference 0. So this is not subtraction, this is actually set difference. This is a set and this is a set. When you give minus, it means it is set difference. It means R, the real number set is excluding the element 0. G is equal to R by element 0 is nothing but the real number set without 0. So let's take for an example what elements does G contain. It can have 1, 2, 3 for the positive side and it can have minus 1, minus 2, minus 3 in the negative side. H is equal to minus 1 comma 1 and this is also a group under multiplication. So H contains 2 elements minus 1 and 1. In order to prove this H group to be under multiplication, they say you have to prove closure, you have to prove identity, associativity and inverse. Once you prove all these 4 properties, they say it's a group under multiplication. I'm not getting into those proof now, but I'm just telling you why it is under multiplication. Now we'll just get on to the main part of the question. There's a mapping between G and H. In order to make it very simple, let me take this G in this format for making a map. So minus 3, minus 2, minus 1, 1, 2 and 3. And for H, we'll have it as minus 1 and 1. They have given a function, the mapping function, phi of x is equal to x divided by x mod. It means whenever you present a negative number or a positive number, it ends up positive. So when I apply this modulus to a negative number, it turns positive. When I say it is minus 1, it is 1. When I say it is 1, it is again 1. So when I say it is minus 2, it is 2. When I say it is 2, it is 2. So when I apply modulus, it automatically converts into positive. Phi of x is equal to x divided by mod of x. X is from the set of real numbers. We should not take it for 0 because they have given it is excluding 0 here. So don't take 0 for x. X is equal to 1, which implies phi of 1 is equal to 1 divided by modulus of 1 will give me 1. X is equal to 2. Phi of 2 will give me 2 divided by modulus 2, which is equal to 1. X is equal to 3. Phi of 3 will give me 3 divided by modulus of 3, which is again 1. Now just apply negative elements here. X is equal to minus 1. Phi of minus 1 is equal to minus 1 divided by modulus of minus 1, which is equal to minus 1 by 1 will give me minus 1. Can you understand? Actually, if you don't have modulus, you can just cancel them and say it is 1. But since you have modulus in the denominator, you have to convert it into positive number and then take the division. Now when x is equal to minus 2, phi of minus 2 is equal to minus 2 divided by minus 2 under modulus, and minus 2 by 2 will give again minus 1. Then x is equal to minus 3. Till 3 we can go for both positive and negative to check this. So phi of minus 3 will be minus 3 divided by modulus of minus 3, which is equal to minus 3 divided by 3 and again minus 1. Can you find the solution here? Whatever number you have, it ends up with either 1 or minus 1. Now we will just do a mapping here. All the negative numbers are mapping to minus 1. All the positive numbers are mapping to plus 1. Now we have to find what kind of group it is, whether it is a homomorphism or whether it is one-to-one or on-to, we have to find it. Now let's understand what is homomorphism. When you have a mapping from G to H, this particular phi is homomorphism if phi of G into H is equal to phi of G and phi of H. You would have already come across certain questions that will ask you to apply homomorphism in some kind of equations. So in that you will combine both the equations and give them as a mapping function. The similar way it says once there is a mapping from one group to another group, there is a homomorphism. So not a homomorphism will be out of the option. So now we have to check whether it is on-to or one-to-one or only a homomorphism. Now we will see what is one-to-one. You have A and B here. You have 3 points here and you have 3 points here. When there is a mapping from A to B, B cannot have more than one A. You can have another element here, maybe the fourth element. I can map this here. I can map this here. It goes on. I can have elements left in the B set, but all the elements in A will be used. The thing is, B cannot have more than one A. In this case, they say this is injective. In onto homomorphism or onto mapping, there are two sets named A and B. I have 4 points here, 1, 2, 3, 4, and I have 3 points here. All B elements are used. All B elements in the sense the mapping can be 1 here and 2 and 3. Both the points can map to one element of B and this can be mapped to the last element of B. For better clarity, I am marking the point here. Okay. So here some unused B elements will be there, but here all the B elements will be used and this is called as surjective. Injective is one-to-one and surjective is onto. There is a term bijective, which means it is both injective as well as surjective. This means the A to B mapping will be perfect. Now in this case, we are just using a sample of the real number set. So the mapping of elements is like it is getting mapped only to two elements here. Let's take this to be the A set and this to be the B set. You have more number of G elements and whatever elements you have, everything is going to get mapped only to these two elements. You don't have any B element left out. So one-to-one will not be there because all the B elements are used. You can take this to be onto homomorphism. This is not one-to-one. and homomorphism will be out of the race. Another thing you can take from this is, you can see 1A mapping to one element in 1 to 1. Here multiple A's are mapping to one element of B. So multiple elements in the sense minus 3, minus 2, minus 1 are multiple elements mapping to minus 1 in H. Similarly 1, 2, 3 multiple elements are mapping to 1. So this perfectly sits in onto homomorphism. That's why we are marking option 3 to be the right answer. Next question. Let Z denote the group of all integers under addition. Then the number of all automorphisms of Z is. Integers under addition. This is represented as Z plus. In the previous question, we saw a word about bijective, and in the noun form of bijective is bijection. So whenever the homomorphism is bijection, or whenever it is bijective, when it exhibits both injection as well as surjection, it is called isomorphism. Automorphism is isomorphism from the group to itself. In other words, we can say a bijective map that preserves group structure. Z plus, the set of all integers under addition. If you take the properties for this, you can take the closure property. When you add two positive numbers, say A plus B, the sum will again be positive. Then if you take associativity, so if you say it is A plus B plus C, this can be A plus B plus C. So associativity is also there. Then if you take the identity one, so A plus 0 or 0 plus A, both will be ending up with A. And then for inverse, we have A plus minus A or minus A plus A, both will result in 0. So this is closure, this is associativity, this is identity, and this is inverse. So it has all the four properties. When you take the structure of Z plus group, this group is an infinite cyclic group generated by integer 1. If you want to get the other integers of the group, it can be done using 1. Example, if you have 1, it is actually 1. When you want 2, you can just add up another 1. When you want 3, you can just add 3 ones. When you want 10, you can add up to 10 ones. So every integer can be expressed as a sum of 1 or their inverses. Maybe if you take minus 2, then it is minus 1 and minus 1. So in one or the other way, only 1 will be involved there. The number of ones will decide what integer it will be. So this is the structure of Z plus group. Now we'll get on to the question. The number of all automorphism. What kind of automorphism it has? First, it has identity automorphism. It's a map that sends each integer to itself. And the next one is negation automorphism. It means the map that sends each integer to its negation. If A is there, it will be sending it to minus A. This map is bijective and it preserves the group structure, and it is also an isomorphism because there is one-to-one correspondent between two sets that preserves binary relationship between set elements. So even when you add, it will end up with the same group of Z plus. In this way, we have two automorphisms in Z plus. If map sends integer 1 to A, it must send n. In this case, n will be 10. It means there will be 10 ones added together to give the integer 10 for the purpose of sum of n ones for any n. So there are no other integer to satisfy this, and so no other automorphism, because whatever happens will happen between 1 and the number of ones. So in this way they say it has two automorphisms, one is identity and another one is negation. We mark the number of all automorphisms to be option number 2, 2. Next question, let R is equal to X that belongs to set of natural numbers. X is a multiple of 3 and X is less than or equal to 100. S is equal to X is a multiple of 5 and X less than 100. So here the limit will be 1 to 100 and it must be in the multiple of 3, and S will be 1 to 99 and a multiple of 5. Let's write R here. 3, 6, 9, 12. Since it's a multiple of 3, I can have 90, 93, 96, 99. Even though it has 100, I cannot take 100 because it's not a multiple of 3. When you take S, you have to end it up with 99. So let's have 5, 10, 15. Then it goes on till 85, 90, 95. It ends up here. What is the number of elements in R intersection S and S intersection R? Let's have R intersection S. When you take multiple of 3 and multiple of 5, both are actually prime numbers. When you want to take the intersection, you have to take it in the form of 3 into 5. In fact, they will say if you take the LCM of 3 and 5, it will end up in 15. So when you want to take the intersection, in 3 or in 5, you have to see the multiples of 15. So here you have 15. So I can take 15. Anything below 15 you don't have. You don't have 5, you don't have 10 in 3. So if you take 20, it won't be there. 25, it won't. 30, it will be there because 10 3s are 30 and 5 6 are 30. So 30 will be there. Similarly, 45. So 15 3s are 45 and 5 9s are 45. Then we have 60. 20 into 3 60 and 12 into 5 is 60. Then we have 75. Then we have 90. We cannot go more than this because the next number will be 105. The limit here it is 100 and here it is 99. So we are stopping with 90. How many numbers do we have? We have 6 elements. This is for R intersection S. Intersection is commutative. So R intersection S will be equal to S intersection R. R intersection S has 6 numbers and S intersection R has 6 numbers. The question is R intersection S into S intersection R. So 6 into 6 will give 36 elements. So option number 1 will be the right answer. Next question, consider the following statements. Let's have a general statement here. Any set with the given operations, if it follows closure property, it is called as algebraic structure. When it follows closure property and associative property, it is a semi-group. When it follows closure, associative and has unique identity element, it is called a monoid. When it has closure, associativity, unique identity element and then inverse for each element, it is called as a group. When these properties closure, associativity, identity, inverse hold as well as they follow commutative law, it is called as abelian group. Now let's see the statements. The identity is unique in any monoid. Only when you have unique identity element, it is called a monoid. So A is true. A monoid is a group if there exists inverse of each element of monoid. So when you have closure, associativity, identity and inverse property, it is called a group. So a monoid is a group when there is inverse. B is also right. Semigroup has closure, associative and identity properties. When you have closure and associative property, it is a semigroup. So it has both these properties. Once identity comes inside, it becomes a monoid. So C is not correct. When you have all these properties, this becomes a monoid. If you don't have any idea about quasi-group, let's solve with this. When you exclude C, all the 3 options will be removed. So option number 1. A, B and D only will be the right answer. So from this we can understand quasi-group as closure property is true. But what is actually a quasi-group is it resembles a group in the sense that division is possible. Since division is possible, it has cancellation property. Let me just tell you an example for this cancellation property. If AB is equal to AC, let me cancel A and A. This will say that B is equal to C. Only when it satisfies the closure property, it comes under the algebraic structure. So quasi-group as closure property will be obviously true. Next question. Match list 1 with list 2. What is PERT? Program evaluation and review technique. It is used for unpredictable, non-repetitive activities. PERT is used for non-repetitive jobs. Jobs or activities both mean the same. So A is mapping to 1. Two options are ruled out. Next we will go for CPM. CPM is critical path method. CPM is used for predictable and repetitive tasks. CPM is mapping to used for repetitive jobs. C2. Actually, if you can see, C and D are mapping to the same option. So mostly you might not have third option. Let's check. Then they have given two times, optimistic time and pessimistic time. So optimistic time means you can just remind the term to optimal. Anything that is being completed in a short time. So in this aspect we are mapping B to 3. The shortest possible time to complete the activity if all goes well. Pessimistic time. The longest time that an activity takes. So D is mapping to 4. So as I told, third one is ruled out. Option number 4 will be the right answer. So with this we are completing Unit 1 questions.